starting first with Jeremy Hochman and Scott Blair from Megapixel, who will tell us about how the Eurovision Song Contest transitioned from Baseband to ST2110. And if you know something about the industry, Eurovision Song Contest is not something you hear about very much in terms of their production. They're very conservative, so I was very much looking forward to this presentation, and I'm looking forward to learn more about what this fine gentleman will tell us in terms of their production. So please take the stage, and we're all yours.
Sure. Thanks for having us. I've been standing all day, so I'm going to sit down. We'll have a conversation. We are going to talk today, as described, about this transition to 2110 at Eurovision this year. I am Jeremy Hochman, founder of Megapixel. We innovate in visual technology. We've started the company since 2017. I've been personally involved in the LED market for over 20 years and have built LED processors for the last 20 years. And Scott.
And I'm Scott Blair. I'm the VP of Product Management at Megapixel. I've been in the industry for about 30 years. A good part of that time was spent over on the lighting side of the industry before transitioning into the video and LED side a number of years ago. And I've also been very involved in writing technical standards, protocols for the entertainment industry on the lighting side. So, some of that will kind of come into play in the conversation here as well.
Thanks, Scott. So I want to go over just a couple key facts and some backstory on Eurovision, because I think it's important to understand this from a planning perspective and how we were starting to think about the project. So Eurovision is a very massive broadcast event. The planning starts about 2 weeks after the previous year. So there's quite a long development path for getting technical suppliers onboarded, bringing in new technology. And typically they really like to bring in new technology and deploy it, because it ensures that the manufacturers are actually on site and bringing in the direct support. This was the first time since Russia in 2009 where there was a single supplier that was responsible for lighting, sound, video, and broadcast equipment. So that gave us kind of a unique opportunity with de-risking certain things, about being very ambitious. And that supplier was Creative Technology, part of NEP Group. And we have a very strong relationship with them. And so that was a key factor in our ability to kind of push this initiative. We've been involved in Eurovision since 2021. The production itself is always pushing new technology. And for this particular year, they wanted to run the entire LED system on 2110 for the first time. So we were onboarded very early and worked closely with CT to validate a lot prior to load in. So we had many months of testing to be able to make this as seamless as possible. And then Eurovision has been increasingly using LED because of the low power mandates, and so no non-LED fixtures have not been on the show since 2022. Scott, do you want to talk about some of the pain points?
Sure. As Jeremy's talking about, Eurovision, it's just a massive production, and they really love to push new technology. It really is the Olympics of production design. I've been around Eurovision for about 20 years with other manufacturers, with new products supporting on it. And they've always really pushed the limits of technology and trying new things. And so there's a lot of risk with that, and you have to manage that risk and, be able to de-risk it, because at the end of the day, you've got to have a successful, broadcast that is going to, all of Europe. It's like the Super Bowl is over here. It's just, it's a massive, massive production over there. And so one of the first things, was we started discussing about doing, SMPTE 2110 end to end for the entire production. I was all on board. I had one requirement. My one requirement was that they had to do, there had to be a lot of testing before, we rolled in, because with 2110 still being a relatively new standard in our industry, we've had a lot of experience with it, but we've not necessarily done interoperability and used every other piece of gear out there on a show before. So in this case, it was going to be the first time that our processing was using 2110 talking directly to the disguised media servers. So it was really critical for us to do full-scale interop testing, long before we get to the point of rolling into the arena. And, that was the requirement I pushed in our initial calls with all the different teams. And fortunately, everybody was fully on board with that. And CT were great partners in facilitating having all the testing at their facilities and providing all the gear to be able to do, a full-scale load testing. And so then by the time we rolled into the production, everything just went together smoothly. Once we got to the arena, there was no challenges. It all just went together, which is what you want. You don't want to be discovering new things and finding your problems for the first time when you get on site. The 2110 overall also, really, while it brings complexity in one area, it brings great simplification in others because of the elimination of all of the different signal conversions that had to happen in normal broadband video. Normally going between SDI and HDMI and DP, you've got added latency, color space conversions, everything else. So this really gave us a lot more flexibility. You also have a lot of limitations with the baseband formats of length. I've worked on a number of big shows before where even you have plenty of backroom space, you end up playing road case Tetris to try and lay the backstage space out to meet within running a DP signal between racks at 4K with tight limitations. So making everything Ethernet greatly simplified things as well and gave better scalability. Obviously, being able to consolidate, the streams over, single network. So instead of having a massive, rack convert, you've got to convert all of your media servers from DisplayPort typically to SDI, and then you've got a big, massive core router that everything has to run in. Instead, everything just lived on a network. So you could go into the switch on the top of the rack and easily distribute everything from there.
So now that we've talked a bit and looked at some bullets and talked through these pain points and advantages, I'll show some pretty pictures. This is one of the views of the stage. There was a massive backdrop of LED. There were also cubes that moved up and down. Each one of these was independent 4K rasters that were sent into the processing. And so you can see how massive the arena is with all of the different display surfaces. One of the things that's not necessarily known either as an audience member at the same time as the broadcast or vice versa is that a lot of the scenery is set up for close-up shots. And so if you think about the last image that I was on showing that big open view of the arena, this is a nice camera shot that's very close up, and so it's more intimate, but it's less meaningful as a spectator in person, and all of these things need to be accommodated for. For these very small, let's say mini sets, things have to get moved and changed over on the set very quickly, and we've got a video that I'll show of that as well in a second. And then this is the front of house view. You can see there's a massive control system here. If anybody has been to a concert before and seen front of house, this is basically like running 10 concerts all at the same time. So this is typically not a picture you'd see, watching the broadcast, but it's pretty cool, and there's a lot of camaraderie on the set. So one of the things that was really cool this year is there was a practical LED floor. Of course, it was doing really cool things from a video perspective, but it was also color coded to let everybody know where to move set pieces to. And so these color codings allowed for a very quick changeover. Again, very similar, as Scott mentioned, to a Super Bowl halftime show where everything needs to come in and come out very quickly. That was accommodated. This is an example of an artist changeover where I'll probably let this video play. It's about 30 seconds. You can see the videos changing on the floor, so they know where to put things. They've moved the drum kit in. They're about to focus the lights. And so this is a completely new act. Could be a new lighting designer, new scenic design, and all these things. And it's basically stepping through cues so that they can understand what is working and what is not working on the set. They even test the pyro. They're finishing all their polishing and dusting of the floor. and then in a few seconds, they're going to start and they're rolling right into it. And this is captured live. So, as fast as this video has played, they have transformed the stage completely, and now they're into an act.
And it's like this back to back to back. So you can see like there really is just no room for error. It's all got to work every time.
Yeah. So these are some amazing lighting cues happening, and this is, very massive changeover very quickly. So let's dig into a little bit of the network planning. This is a view that, Scott, maybe you can talk through, both the physical, topology as well as the network plan.
Sure. So, as you can see here, there's two networks. Redundancy was critical, obviously, for this type of application. So they're running a full red and blue, primary and backup, network. So we had full redundancy in everything. Even the LED tiles, have redundancy, between two different processors to those. Also, as you'll note here, physical redundancy in the cable layout is also critical as well. Taking different paths for your cable routes for your main and backup is also important in any type of big project as well, because if we have two cables that are, right next to each other, if one of them gets physically damaged, there's a good chance the other one might get physically damaged. Got a great story about that. About 5 floors down in this very building for the Oscars a number of years ago, where there was a big LED set cart tracking on and off stage. And during rehearsals the night before the live broadcast, on that show, they were running the primary and the backup separate fibers, but through the same TAC-12 cable. Set cart runs over the cable because they didn't page it off fast enough because they were tired from running the queue all day long. And it shredded the fiber cable. And so there's your main and backup are all gone in one shot. So, this is a good example of a practice of, running, diverse cable paths for your redundancy, just to ensure that, you've got, good reliability and you don't have the same physical damage occurring to both systems.
So that's our PSA is redundant physical paths as well, not just,
logical.
Not just logical. Yeah.
And then looking at the network diagram here, so you can see on the left we basically have all of our sources feeding through 2 core switches to all of the LED processors there on the right. So you'll notice here that there's a red and blue network, so we're getting primary and backup feeds. There's a primary and backup switch, basically a red switch and a blue switch. And then also you'll notice there's a little line drawn between the 2 switches. So this allowed us to have, for each of the processors, even though we had a physical, red primary system and a blue backup processor that was feeding the same LED tile, we also, each processor had an additional level of redundancy in that it was subscribed to both the feed from the red system and the stream from the blue system as well. So this allowed us actually, to have multiple levels of failure that could have occurred without knocking everything out. We didn't have to be solely on the red system or solely on the blue system. We could actually sustain, multiple cascaded failures if needed, without it ever impacting anything on the stage. Here's an example of how seamless redundancy works with the LED screen itself. So as you can see, we've got our Helios primary processors, feeding white content in this case on the left, and then let's say our backup processor is feeding a blue image on the right. And the way seamless redundancy works in our system is also very similar to the way it works in 2110 as well, between the red and blue networks in 2110, is the tiles are listening to both processors and consuming data from both at the same time, for every frame of video, for every packet. And whichever one gets the packet there first for that given portion of a video frame, whichever processor happens to get the packet to the tile first is the packet that it'll use. So that means I can literally have 50% packet loss, on one processor, and those will then get filled in seamlessly with the packets coming from the other processor instead. So in real life, if I'm actually actually feeding different content from the two processors, what I would see is something like what we've got on screen, where part of some of the tiles are white and part of some of the tiles are blue. And this is really the same way that 2110 redundancy works as well, is you've got simultaneous communication of both streams coming in, and it's taking whichever packet gets there first to give you seamless redundancy. So if you lose packets, they get filled in by the other, and you don't have dropped frames or stuttering video in that case.
So one of the things that was pretty cool about this show, we were in a venue that actually had very little backup house space. And so moving to 2110 also, by having that large network infrastructure, removed so much equipment from backstage that we were able to fit everything in the racks that you see there in the photograph. So the entire stage and all of that equipment that you saw running on broadcast is just in a few racks here. And this was actually just behind curtains on the other side of catering. So it was literally, cohabitated with a lot of other things in the building. And that's the benefit that we gained from the 1.4 terabit network. We were running, the show was 10 disguised servers, 14 Helios processors, including, cold spares, the 3 core Arista switches, and then a whole bunch of downstream, networking equipment and, monitoring. And speaking about monitoring, because everything is network based, there are a lot of extensible APIs that could be used also to give confidence dashboards for the actual live state and running of the show. This particular board was built out by NEP, and it's showing basically a whole bunch of network status, and things could change from green to yellow to red, et cetera. And we also had a nice network bandwidth dashboard to show us how close we were getting to the edge and that sort of thing. So all of these types of statistics would never be available on a traditional baseband system. But here we're able to poke at basically every single signal along the chain and see what's happening. Here's another view with some gas gauges. So different people in different departments wanted to see information displayed in a different way. And again, the APIs allowed for all of this very extensively. So we've got a couple very simple slides here showing a traditional data path. This would be running SDI or an HDMI workflow, for example, where we may have stored footage going into a media server, going to a video router, going into the LED processing. They all need their own discrete Genlock signals that feeds into the LED wall, and then we have camera, and we have DIT for film, sometimes broadcast as well. These are all failure points, right? Every single one of these is serially connected, and if any one point fails, I don't want to say the whole show fails, but a lot of things fail. Whereas with 2110, we love it because everything goes into a core switch. The video router becomes the switch as well, and everything is greatly simplified.
I think one other point to that also is, as we were showing with the dashboards, we have complete monitoring of all the devices in the system and visibility if there's anything that's not working or anything that's having an issue in real time. Whereas with the traditional video system, where you're chaining one device to the next, you may have an outage or a problem at some point, but you're not necessarily clear right up front which device is it occurring in the chain. By not having devices all chained together serially, it makes troubleshooting a lot easier as well as better instrumentation for diagnostics.
And just to comment on the network diagram in general that we've got up here, I don't expect anybody to have like Superman vision to read everything that's on there. But I think the main bit of importance here is that this is the entire system topology for the entire show on one page. And typically it would be 25 pages of riser diagrams.
Yeah, again, showing all the devices, one connected to the other and everything else. Whereas really everything here, we just have everything as nodes on a network connecting to, different distributed switches.
So on the LED processing portion itself, we were using 100 gig native fiber input to our Helios processor. You'll note that the back of the unit looks a lot more like a piece of IT gear than it does video equipment because we foresaw this IP-based video coming when we were developing the product. So it's basically loaded up with a whole bunch of SFP slots. And the unit will take 8K native sources, and we can do that as single 8Ks. We can also stitch multiple 4Ks together in different formats, so you can stitch them to make an 8K by 4K, but also very often, especially with virtual production, we'll do very wide rasters and go up to 32K, and that's all in that 1RU appliance, which makes the rack density pretty great for efficiency from that earlier photo, and it's pre-tested with a whole bunch of gear at this point. Scott, do you want to talk about the benefits of 100G versus
Sure. I mean, a lot of the things we've covered. Certainly reduced latency is a big thing. Again, having everything on a high-speed network, running at wire speed, you're able to, have packets going through, in real time through the switches. You're not adding frames of delay or, sometimes multiple frames of delay at every device in the chain. So by having everything just connected to a core switch and being able to process that quickly, it really just eliminates the majority of the latency you might have in a complex video system going through video routers and signal conversion, everything else. Also, we get much more reliable metadata. So because 2110, you're able to stay in the same color space the entire time, and that color space and metadata for the frame rate and the resolution is all communicated through the system. Everything just knows what it's supposed to be at, and you don't have, loss of data through the system. A good example is with, signal processing. If you're doing something in HDR, you might have a screen switcher that doesn't know anything about HDR, and so it strips the metadata off in the middle, whereas we're able to preserve that all the way through the system. Obviously, we talked about the monitoring capabilities, and I really can't, emphasize enough how important and how critical just on any show good monitoring is, because it allows you to diagnose the problems long before they're actually visible to the eye. And so that's one of the things we really focus on a lot of projects we do, is being able to have really good monitoring platforms that allow us to see problems in the data and have alerts long before a visual glitch ever shows up on the screen.
Yep. And so this is one of the UI images from Helios. On the right-hand side, you can see the metadata coming in on one of the 2110 streams. But again, just showing that we've got a live view of the tile map. We know which ones are online. We know which ones are offline. And we understand what's supposed to be happening in the system. And so one thing that I think is really important to call out here is, a lot of people think about 2110 and NMOS and the network control for video, but all of these systems are important, right? We should be thinking about not only video, audio, and LED, but also potentially rigging and other types of cameras and tracking and different servers, communications, pyro. All of these things living on a network gives a tremendous value, because it lets us do things creatively on the network that we used to not be able to do with all of these systems that were, not really meant to go together. So I've got one kind of closing example here, which is camera cutting. So this was all done in an automated way, all with network control, and this was triggering off camera cuts, pyro, lighting, video, various facets of the LED system. And so when I go to this next slide, you'll see this video start to play. And watch how fast the cues are happening for both the camera cut that's well timed with the pyro. And there's no way that a human could do this in a repeatable manner, let alone maybe once. Yeah, pretty awesome cues. I think we've got a few minutes left for Q&A, so I will leave it to the audience. Thank you for listening to us.
Thank you. you very much. Do we have any questions in the room? Yes, we have.
Thank you. You made some great comments about 2110, about the implementation as well. What was your point of view about NMOS orchestration and how it pertains to doing NMOS specifically for such an event over a short period of time? Was it worth it? Was it not worth it? Were you able to use specifically 2110 without having to do NMOS in the end? What happened for the workflow?
I think we looked at it as a great opportunity because we had when we went into this, we didn't have our NMOS implementation complete at that point. We've been using 2110 very successfully for a while. In a lot of the applications we were in, there was really no need for NMOS. But this was a great example of where NMOS would be tremendously useful. So we used it as an opportunity to push our development to fully implement our NMOS solution, and they were able to take advantage of that. So it was very helpful for them to be able to get all the data back from the system through NMOS, to have the dashboards and everything connected. And we've made great use of it in some other applications since then. So there's still some challenges with NMOS when you're dealing with a device that can have multiple different streams coming in. Our processor, for example, we have 100 gig input on it. We can subscribe to currently 4 different streams coming in. And with NMOS, it doesn't necessarily have the connotation it has a connotation really of one device, not kind of treating it as 4 separate devices. So there's still some challenges there, especially if you're doing your NMOS connection over the media network versus the IP network. So to address some of those challenges, we've implemented the NMOS control over the IP or over the LAN network, the control network, which is what we're finding most others are doing. We've seen some out there that implement it over the media network, but then that gets more challenging from a network infrastructure point of view and how you're routing things. And when you've got something that can handle multiple sources and has to present itself differently to each one, then.
Yeah, I think it's definitely a rabbit hole of a conversation. I think it's very good for a lot of the traditional control to be able to have kind of one control infrastructure that's able to touch a lot of equipment. But it's going to still require a lot more interoperability testing for understanding what types of devices need to be controlled.
Any other questions?
I have a question.
Yeah.
So there was a lot of redundancy. How much was it that you actually ended up using? So what was the most major failure on air or during the preparation? So when the redundancy had to kick in, to which extent?
I'm not sure that there really was. I know there was occasionally some issues with like P2P synchronization that occurred at different points with a processor here or there, but I'm not aware of any issues during the broadcast itself that came up.
Yeah, I was going to say the same. I'm not aware of a single issue where the backup actually had to take over in an automated fashion. I think, interestingly, what we see the most, both from a broadcast and film production perspective for main and backup, is it gives the flexibility for things like media servers to get rebooted or new media to get loaded on a backup or let's say the main server, where we can seamlessly switch over to the backup to continue playing and doing things.
And in the best systems, while you've got good instrumentation to know if a problem has occurred, in the best systems, you don't ever see it on the screen, right? Like everything just runs seamlessly, and it's only after the issues occurred that you realize, oh damn, like something happened here, but everything was fine.
That's kind of what was hoping for.
Yeah, that's what you want it to be. You want to be aware that something did happen, but nobody else is aware that anything happened.
Yeah. Oh, we were running for 30 seconds on backup 5 minutes ago and nobody noticed. Type of thing.
Very cool. Any other? We have 1 minute for a last question. No. Oh, there. I'll run this time. Okay, you take it.
Sound. There we go. When you mentioned you had 4 streams on a 100 gigabit interface, that infers you weren't using JPEG XS, or were you?
Correct. Everything's uncompressed.
Okay.
Yeah.
And that decision was made because you knew what your bandwidth requirements were ahead of time?
Yeah, in our system, we generally always are running uncompressed because we typically are stitching signals together. We're also stitching thousands of tiles together into one singular array. And we find that any of the compression algorithms, when they're touching smaller chunks that need to get tiled, it's not predictable for us for what the edge boundaries are going to look like. And so those actually become quite visible. So we work only in the uncompressed space at the moment.
And last question, did you just use a single dual spline, or did you have leaf switches underneath that?
I believe that they had everything fully connected in a dual spine.
Okay, very good. Thank you, Jeremy and Scott.
Thank you all.
Very insightful.
Thank you, everybody.